difficult. Anyway, if you are familiar with T-joins, okay, but let me ask you, so how many of you are familiar with T-joins? Or say, if you haven't heard a T-join at all, please let me know. Okay, so I will start with the definition, but I understand that most of you are already familiar, okay, somehow. Okay. So T-join. So anyway, we have a graph. Okay. So I should write T-join is a concept on undirected graphs. So here we use the notation of the vertex set V and edge set E. Now, in addition to the graph, we seem to be given a T is a vertex subset of even cardinality. Okay. Now, J, the subset, edge subset J is said to be T-join. Okay. Okay. If the degree of J, V, is equal to odd if V is in T, and even if V is not in T. Okay? For every V, for every vertex V. Okay? So here I use this notation dj of V, which means okay, so here's a vertex V, and some of the edges incident to V maybe are edges in J. Okay, so the number of edges in J that is incident to V is denoted by that way. Okay, now for example, if I have a graph like this one, and I put T, for example, by these 4 points. Okay, so T-join, one of the T-join be like this shape. Okay, so here's degree is 1 exactly in these red points, and other points the degree is 2 or 0. Okay, so this is an example of the T-join. Now, when I talk about T-join, I should also mention about T-cut. Okay, so T-cut is actually a set of edges that collects 2 parts. Okay, so assuming that this S, and this is V minus S, and assuming that S of T, the size of the S intersection T is odd, then I said that this delta of S, which is the edge set, edges connecting S and V intersection S. Okay, so these edges is called a T-cut. Okay, now how these two concepts are related? So here's a very important fact, that for any J, which is T-join, and for any C, I should write not C, maybe K, which is T-cut, then so any T-join and any T-cut must intersect. Okay. So is this clear to you? I said here's t. So the number of t points are odd, the number of t points are odd here. Okay? And you can sum up this. So in the t join, I said this degree at these points are odd. Okay? In the other points, the degree is even. So if you sum up the degree of these, if you sum up the degrees over all these points, okay, all these vertices, then the sum must be odd, right? Yes, it's odd. So therefore, there must be at least there must be odd number of edges that comes to this way, okay, in the t join. So therefore, there must be intersection, non-empty intersection between any t join and t cuts. Okay. Now, the concept of t join was introduced in the early 70s by Edmonds and Johnson when they wrote a paper about entitled Matchings, Euler Truths, and the Chinese Postman Problem. So, okay, so the concept is quite related to Chinese Postman Problem. So let me explain what it is. So in the Chinese Postman Problem, we are given a graph, undirected graph, and the question is we want to know how to visit. How can we? So we want to find a tour that visits all edges at least once. Okay. If the given graph is Eulalian, the answer is trivial. Oh, I should say. So in the Chinese Postman Problem, I want to find the minimum length tour that visits all the edges at least once. Okay. So if you are given a graph like this one, okay, this is not Eulalian. Okay. So because we have these points, okay, this is odd degree. This is odd degrees, okay? So therefore, this is not Eulalian. But then, we can think of this a minimum length t join in this graph. Now, for example, okay, in this case, for example, this may be your minimum t join, okay? Then we can add these yellow, say, sets to the original one, okay? Then the resulting graph should be Eulalian. Okay, so we have a say tour in this graph, in this augmenting graph, and they show that this gives you optimal solution for the Chinese Postman Problem. Okay. Now, but the problem is how to find the minimum length t join problem. Minimum length t join, and for that problem, they devised LP formulation. Together with a primordial algorithm for solving that problem. Okay. So I will write down the problem. So given a weight on the edges, okay, I assume it is non-negative, and I want to find the minimum weight. Okay, so what is the minimum weight? W of j, where j is a t join. Okay, and here I write W of j to be the sum of the weight in the all edges in j. Okay, and I will just use the notation nu t w. Okay, to express this. Now, to find such a minimum weight t join, I said Edmonds and Johnson introduced the following LP. Okay, so minimize subject to the constraint that x of e Yes, you're right. Very good. S in Q of t, and still I miss some notation. Q of t, what is Q of t? Now, let me define Q of t. Okay. Is a S of, okay, R S and T is odd. Okay, this is the notation. So I assume that we are, so we can arbitrarily pick a vertex R, okay, in this graph, and collect all these, say, vertex subset S, which has odd number of T points. So like 1, 2, 3, 4, 5, 6. This is a T, this is T, and this is the one S. Okay, so we can think of all this collection and denote it by QT. Okay, so the number of, so the size of this QT is exponential. So this linear programming has a exponential number of inequalities.
So you want to say delta S somewhere?
You're right. Yes, sorry. Here. Yes, thank you. Okay. Okay, so the point is, okay, so I should explain. So imagine that XE is 1 if E is in J, okay, and XE is 0 if not, okay. Then, so this means that your T join, okay, must intersect with a T cut, okay, because the delta of S will give you a T cut, okay. So you just write down these conditions, okay. But they say, but the point here is that if you forget about the 0-1 constraint, okay, then this LP also gives you an optimal solution for this combinatorial problem of finding T joins, okay. And to do so, they actually describe a primal dual algorithm to solve this problem, to solve this LP. And at the end, they could show that there is a 0-1 solution. There's a 0-1 solution is obtained. Okay, so by this way, they show some kind of integrality result for that. And the algorithm is actually efficient in a sense of the polynomial time complexity. Okay, that's what is known about T-join. And I should also mention another characterization for minimum weight T-join. Okay, is by André Chebu. Okay, so he says that André Chebu. Okay, a T-join is of minimum weight. So if and only if the W of C intersection J is at most WC for any circuit. Okay, so this is not actually hard to prove. Okay, in both sides, but maybe because of the time constraint, let me skip. Okay, and the proof. Okay, you can. I think you can easily prove that. After all, and I will mention this result later a little bit. Okay, so what's new? Okay, in this talk. So I would like to think of the next kind of the next kind of problem. Okay, so suppose we are given G and W. Okay. Now I want to find T of even cardinality maximizing nu T. Okay. So this, as I wrote before, nu TW is a minimum of Wj, where J is a T joint. Okay. Okay. So here we are given a weight, and I don't know what T is, but if you are given T, then we can compute minimum weight. So the problem is to find T so that the minimum should be maximized. Okay. Now what's known about that? And so I will write down four results. Okay. First, for tree, if G is a tree, if G is a tree, then it is easy to solve this problem. Okay, but okay, and also if the weight, if W is uniform. Uniform, I mean that every edge has weight 1, equal to 1. Okay? Then, there's a minimax theorem. Okay, I should write. Of Andras Frank in 1993. Okay, and so I will explain this theorem later. Okay, and because of this minimax theorem, based on this minimax theorem, he gave a polynomial time algorithm to solve that problem. Okay, if W is uniform. However, in general, the problem is NP hard. Actually, it is NP hard even on a cycle. Okay, I will explain this later as well. And finally, we find a 2/3 approximation algorithm. So these are all what I want to talk to you in the next 35 minutes. Yes. Okay. So first, so tree, if G is tree, this is easy. Does anybody have a clue?
So you take, so you count the number of leaves and if number of leaves is even, then put them all of them in. No, that's not good.
Okay, here's an example. Pardon me? Induction? Even more easier. Even easier. Okay, so I will, for this particular example, I will write down the answer. What is this?
They are the ones that have distance one from the leaves.
No.
All correct.
Right.
Do you have a circle one but it's a degree 4?
Oh, I made a mistake. Good. sorry. That's why you came to that answer. How tricky I am. Okay, good. So these are the vertices of all degrees. Okay. Now, if I set t in that way, then I want to claim that our minimum weight t join, okay, must be the entire tree. Okay. Because if you take an arbitrary edge, then and delete it, then you have a cut, right? So in this cut, if you count the number of the number of the sum of the degree in the right side, okay, must be odd because it has only one edge across this cut. Okay, so therefore your number of t nodes here must be odd. Okay, and therefore this is a t cut, and every t join must intersect with t cuts, with any t cuts. So therefore we must use this edge. Okay, we must use this arbitrary edge. So that means the entire solution is for this minimum weight t join problem for this t is the entire tree, but that is of course attains the maximum. Okay, so this is an easy solution. Okay, so this is done. Now next, so let me mention why it is NP hard on the cycle. Oh, actually I should mention that, say, despite of my career nearly 20 years, I always find myself quite poor at proving these things. But I have good friends, so I asked Anders Frank. I asked Anders Shaboon if this is because I already have this result. Okay, but I was nervous if it can be solved in polynomial time. The approximation result is nonsense. So I asked Anders if this is an NP hard or no. And a few days later, I got an email from him. Okay, and he said you can relax.
So you write a joint paper every day?
Oh, good point. So I should mention that I'm talking about a joint work with Ravi. Ravi from CMU. Okay. And, well, yes. So this is actually an easy remark. Okay. So NP hard. So I will tell you why this is NP hard, even on cycle. Okay. So here's a cycle. Oh, it was too large. Okay, not too many points. Cycle, and we have weights. So weight W1, W2. Wn. Okay. Now I want to find a T so that the minimum weight T joint in this cycle must be maximized. Okay. Now suppose we can solve this problem. Then we can solve this other problem, which is suppose we are given W1, Wn, which is okay, the rational numbers, and I want to decide. Oh, where is my? Okay, I want to decide or find J of E such that okay. The question is decide if there is a set J. Okay, such J of 1 to n such that okay, so W of J is half of the entire. Okay, this is a well-known NP-hard problem called partition. Okay, now the point here, and I want to claim that actually the T-joint max mean weighted T-joint problem in this cycle is equivalent to that problem. Okay, because if you take any subset of okay. Okay, so let's take J is any subset. Okay, then you can think of the vertices which J has an even degree. Oh, sorry, odd degree. Okay, these are T, and then J is a T joint. Okay, and also E minus J is also a T joint. Okay, so because of that property, we can solve this problem. Now we came here. Okay, let me explain the next 7 minutes what is known about this unweighted case.
Can you do?
Oh yeah, okay. The keyword is the joints and ears. Okay, so here I need some new terminologies. Okay, J in the undirected graph is called joint if and only if for any circuit okay, for any circuits, its intersection with C is at most half of the cardinality of the length of the circuit. Okay. Now we denote mu G by the maximum cardinality of a joint. Okay. So let me mention first that this is related to this T-joint problem, T-joint, because if you're given J, okay, then we can always pick up J, pick up T. T is the set of vertices where the degree of J is odd. Okay, then we have T. J. And in that T obtained by J, we know that J is a minimum TJ join. So J is a minimum TJ join. So J TJ join. So because of the definition, it's clear that J is a TJ join. Okay. Now we have this property. Okay. So I wrote somewhere. I wrote here about the theorem of under Chebu. It said that say a T join J is optimal, is minimum weight, if and only if it has the weight properties. Okay. And here the discrete, yes, weight property of that. So that ensure that so a join is a minimum TJ join in some sense. So and if we okay, on the other hand, if we have a yes.
Circuit here is the same as cycle?
Oh yeah, cycle. So cycle means a single cycle, right? Yeah, okay. Yes. Yes. Here, there, I said cycle. Sorry. That. Okay. So because of that, the maximum also. So this problem, maximum cardinality of T over join, actually is equivalent to the problem of finding the maximum cardinality of a T join of sub T. Maximum cardinality of a minimum T join of any T of some T. Okay, so that corresponds. So if we can solve this, if we can compute this mu of G, then our problem is solved. And this, say, Thelman, Rush, Frank, actually, okay. Tells us the following. Okay, I still have some time. So are you familiar with ear decomposition? Okay, so ear decomposition is just a decomposition into ears, of a graph into ears. So it has say sequence G0, G1, G2, or GT, which is equal to G, and G0 is just one vertex, one vertex, and no node, no edges, and GI is a GI minus 1 plus a path. PI, whose ends are in GI minus 1. So you start with 1 point, add a path. Okay, this is G1, another path, this is G2, G3, so, okay. And if you obtain your graph in this way, and it is called the ear decomposition of your graph. Okay. Now, you introduce a quantity called phi of G, which is a minimum number of odd years. No, sorry, even years. Even years in a year decomposition of G. Okay. So actually, given a graph, so you can think of many various kinds of year decompositions, and the length of this year decomposition, the number of paths, is always uniform. It's always invariant. But here, I want each path to be odd lengths, to be of odd lengths. That means the number of edges is odd. Okay, and so phi g is the minimum of that. And while this is so interesting, the first reason is that there's a theorem by Lovers in early 70s, which says that G is hypermatchable. Okay, if and only if phi G is equal to 0. So that means that if you have the G is hypermatchable if and only if you have an ear decomposition where all the paths, all the ears are either odd lengths, all lengths.
You want to define the hypermatchable?
Oh yes, I will define that. What the hypermatchable is. Okay, so a graph G is called hypermatchable if for every vertex V, G induced by the induced subgraph, or say if you delete V of G, if you delete V from G, then that has a perfect matching. Okay. So to ensure the property V, the conjunctive V must be odd. Right. So here's an example of a hypermatchable graph. Okay. And it in these have ear decompositions. For example, starting from this is odd. Okay. This is odd. This is odd, odd, odd. Okay. And at some point, so this phi of G is shown to be equal to the number of edges, to the minimum number of edges whose contraction will make it hypermatchable. Okay. And that's also proved in the Anders Frank's paper. Now the theorem of Anders Frank, 1993, is that phi of G is equal to the twice the mu of G minus V plus 1. So phi of G is a kind of minimum value, okay, and mu of G is a kind of maximum value of the joint. So this gives you a minimax characterization, okay, and he also gave say order V E algorithm to find such a maximum joint, okay, and a minimum even year decompositions. Okay, now I think I have 50 minutes. Okay, so I would like to explain the last result. Okay. Now I hope you remember the linear programming problem I wrote there. Okay, so I don't repeat that. Now let me think of its TCP is a dual of the LP. What I wrote. Okay, TCP is a maximize. So the dual is maximize star of S QT YS. Okay. Subject to the constraint S is a set where the E is in S and YS is at most. And YS must be so the dual must be like this. Okay. So the property here is mu of T of W. So this is the minimum okay, is equal to the optimal value of Tj. I'm not sure if I wrote Tj, but Tj means the LP, what I wrote here for the minimized version. And because of the LP duality, this is equal to the optimal value of TCP. Okay. Now,
So TCP means T-cut packing?
T-cut packing, yes. Good. Exactly. Now I want to introduce, say, upper bound of this. Okay. Upper bound of this result of this quantity, which is independent of T. Okay. If it is independent of T, then that will give you upper bound of our problem of maximizing the minimum value. Okay. So to introduce, so what is TCP? What is CP? That's cut packing. To do that, all I have to do is just kill it, and together with it, I have to change this to be just S. Okay. Is any subset excluding V, and change this to S to V excluding R. Okay. So that's it. So this LP CP, I mean cut packing LP can be solved in polynomial time. So I should write it down how to solve CP. Well, so how the best way we know is to use the ellipsoid method. Or we can use the extended formulation. So here I will omit the detail, but basically you can think of a larger LP whose projection will become this LP. Okay, so the dimension, I mean the number of variables will become larger. Yeah, but the number of constraints will be polynomial. And I said the number of variables will be larger, but still polynomial. So in that way, we can define a polynomial size LP, okay, whose optimal solution will give you an optimal solution for that one. Okay, so in both ways, we can anyway solve this CP in polynomial time. Okay, and furthermore, this solution has a good property, or actually, yes, I can ensure that it has a optimal solution that has a good property. So what is this good property? I should say, okay. Now suppose Y is the optimal solution opt to CP. And I write psi to be the set of S where Y star has a positive value. Okay. Then I want to claim that there is optimal solution. Okay, lemma. Okay, there is optimal solution Y star such that phi forms a laminar family. Okay. Laminar family, I mean that for any member of this phi, so any pair of members, they must be a subset of each other, I mean included each other or disjoint. Okay. Now, and also actually, if we solve this problem and obtain an optimal solution which doesn't have this property, okay, we can actually simply change the solution, okay, so that the Y star, so the obtained results satisfy this property, okay. So this is, the process is called uncrossing. And the idea is basically, if you have two pairs which has intersection, which are these crossing properties, and then you can think of its union and intersection. Okay, union and intersection, and you can say subtract the value YSI and YSJ by minus epsilon. Okay, and if epsilon is determined to be the minimum of these two values, then one of them will become 0. Okay, and instead of doing that, we also ISJ and YI intersection J to be plus epsilon and plus epsilon. Okay, so if these two are originally 0, then we have a new member of psi anyway. But one is deleted, at least one is deleted. And by this operation, we can say uncross the family. And there is a result by Harken, Lovers, Schreiber, and Taldos in late 80s, who said that this kind of uncrossing can be done in polynomial time. I mean that at the end, after the polynomial number of operations, we can obtain an uncrossing family. Okay. Now, so therefore, I can assume, so I can assert that in polynomial time, I can obtain optimal Y star, which is where the, say, positive values are taken by a laminar family. Now I come to the point, to this. Okay, so let me assume that we have we have a laminar family. So let me write some picture. Okay. So these are laminar families. We have YS. So YS is star is positive. Now, based on that information, I would like to find an appropriate T. Okay. Like this way. Okay. Once I set T, okay, Okay. Once I set t, then I can. So once I set t, there are, okay. So for example, once I set t, then I will take the sum of these members, or the sum of the value for these members, in which odd number of t vertices are included. Okay. If I set this t, then this one and this one is counted. Okay. This one and this one is counted, but when it comes to this one, this has even number of cardinalities. Okay. So why I'm doing this? Because of this difference. Oh, I erased that. But because of the difference of this objective function. So in the CP, I said y is just VRV. Okay. So R is here. Okay. And YS. Okay. Whereas in TCP, I write QT is YS. Okay. Now I get this solution YS, and from that I will restrict this Y star S onto Q of T. Okay. I will restrict this YS onto Q of T, and that will give you a feasible solution to this. So restrict on Q of T, and that is a feasible. That is feasible to TCP. Okay. Now the TCP is equal to Tj, or I should say mu Tw. So if I get appropriate T, so that restricting, say, if I get a T, so that this is as, say, large as possible, which is good. Okay. Now the question is, how, to what extent, to what good T we can get. Okay. Oh, TCP is here. Good. And so the problem is like this one. Basically, I have a tree, because the laminar family can be expressed by tree. Okay. Because I have a tree, and okay, and maybe I can have this. Okay. So these are the points. These are the vertices. Vertices in the union, okay, of these two, of the laminar families, a member of the laminar families, and this is our root, and these inner points corresponds to the member there. Okay. Now, each inner point here has some value. Okay, WS, which is positive. Okay, and I want to set up appropriate T. Select some sets T here, so that the sum of the T, the sum of the weights here of this inner point, whose leaves have odd number of T's, okay, it should be maximized. Okay. Now, I want to claim that the following. First, so to solve this problem, actually we can assume that the tree is binary. Okay. If it is not binary, then we can simply transform it to like this way, and keep the weight here to be here, but the weight here is to be 0. Okay. So that doesn't change the problem. So I assume the tree is binary. The next, for the binary tree,
Yeah,
yes.
For this You wanna make sure that the new vertex also has a odd number of descendants.
No. Oh, but because this has weight 0,
Yeah.
so it doesn't matter if we take it or not.
Oh, I see. So you
Yeah.
only care to no vertices having odd number of t but t descendant.
T descendant, we care of.
Then you add that.
Yes, we add that.
Okay.
Right. Thank you. And now, okay, for a binary tree, I want to claim that there is, I can obtain a subset of leaves. Okay, these are subsets, so the set of leaves, so that for any inner vertex, okay, its descendant has odd number of, say, ti vertices in exactly 2 of the 3. Is it clear what I meant? Okay, I want to claim that we can have a T1 and T2 and maybe other T3, so which may be overlapped. Okay, but okay, there is a certain way to define this T1, T2, T3, so that in each inner point, its descendant has odd number of T1, T2, or T3, or odd number of Ti vertices in exactly 2 of these 1, 2, 3. Okay, the statement is clear. I can tell you the proof very briefly. Okay. Now why? So if okay, we can do actually induction. Okay. So if this is a leaf, if this is a leaf, okay. If you think of a leaf, it's clear. Okay. So I assume this is T1. This is a member. Suppose this is a member of T1 and T2 and nothing T3. Okay. Okay. So what I should do here first. Yep. Okay. Okay, so suppose I have S and P and Q, okay? And if in the subtree, which is called, okay, in the subtree below P, suppose we have T1P and T2P and T3P, okay? And after so below this Q, I have T1Q and T2Q and T3Q, okay? Now, I assume here that the T1P and T2P is of which? Odd cardinality. And okay, T1Q and T2Q. Okay, because if you have these three sets, then we can just simply label so that the T1 and TQ are odd cardinality and T3, T3P and T3Q is even cardinality. Okay. Now we can think of this tree below S. Okay. To construct that, I should define T1S, T2S, and T3S in such a way that, okay, T1S should be T2P plus T3Q. T2 must be T3P and T1Q. And finally, T3 1, 2, 3, 1, P plus T to Q. Okay, and this way, now I said this is odd, this is odd, this is even, so therefore this is odd. Okay, so this is even, this is odd, therefore this is odd. Oh, okay. I can write it down. Yes, okay. Of odd LS. LS is a leaf and a S. TI is, say, 1 or 0. If LS and TI is odd, and this is even. Now, so I can think of I is equal to 1 to sum of this I from 1 to 3, and S is the internal node, so that Y of S all times odd of LS TI. Okay, and this is exactly twice G, twice Y of S. Okay. Because of the property that for each vertex, for each inner point, it has odd. This should be 1, exactly 2 of these 3s. Okay. So therefore, the sum of these is equal to 2 twice the entire set. And so what does it mean? That means 1 of T1, T2, T3 must satisfy this YS odd, okay, LS QI is at least 2/3 of the entire YS. Okay. So which actually means that our solution, so just take this T, such T, one of these T, okay, and the last thing which is tricky is that if the T selected is of odd cardinality, then you can simply add R to T, okay, so that the T will become even cardinality afterwards, and it doesn't change the objective value at all. Okay, and then finally we get S of QT Y star, okay, is at least 2/3 of the S of this B of Y S star. Okay, and I said, this is an upper bound, okay, of the solution, and I said this is equal to the mu TW of the T we obtained, for the T we obtained. So therefore, we said this shows that our solution T is a two-set approximate solution for our problem. Okay, that's the end of the solution. And I should also mention that this is in some sense optimal result. Okay, because let's look at this triangle. Okay, having 1, 1, 1 for each weight as a weight. So the optimal solution for the CP is just take, okay, so 1/2 at each point, at each cut, and this will give you 2/3, okay, whether the maximum minimum weight T join is just 1, okay, if we select these two and collect this, okay, 1. So that means this upper bound, so the LP upper bound CP has a kind of integrality gap of 2/3, okay, or let's say, yeah, 2/3. So therefore, so this is optimal provided that we restrict ourselves to this LP upper bound. But of course, there may be other way to improve this approximate solution, which is we uses other ideas. Okay, so that's the end of my talk, and thank you very much for your attention.